So let's move on to the how this looks mathematically. This is an equation that describes the motion of a spring. I wish I had a neater version of it for you. It's in your book, but as you know, in class I would write this on the board in front of you and talk you through it. But I can't do that on the laptop, so here we are. This is just a leftover from last year. Anyway, what we have here, this is T, capital T sub S. That is the period of the spring, and it gives you the period of the spring in seconds. 2 pi is 2 pi. It often shows up in sinusoidal functions. This is square root, and it's the square root of the quantity of m divided by k. M is the mass of the weight that's bouncing on the spring or oscillating on the spring. That's in kilograms. And then K is the spring constant, which you've seen before. It's a number. It reflects the stiffness of the spring, and the units are newtons per meter. Now, this equation will work for any spring-driven system. It can be a horizontal system where the weight is sliding across a tabletop, or it can be a vertical system where the thing is bobbing on the end of a spring up and down. But that's the variables here. Now, I know you can pause it if you need to, so I'm going to move on to the next page. So here we're going to use this. Here's the equation. This problem we have is we have when the spring is unstretched, when it's just relaxed, it's 10 centimeters long. And then it stretches to 15 centimeters long when you hang a 25 gram weight on it. Now, so that means that the degree of the stretch is 5 centimeters. It went from 10 centimeters to 15 centimeters. So the change in the length is 5 centimeters in this particular case. That's a little ambiguous, so that's why I point that out. That's when we hang 25 grams on it. And what we want to find is the frequency of the oscillation that we will get on this when we stretch it out and let it go and let it bounce for a while. Okay, so the first step is we got to see what we've got. We want to find the time, because if we know the time, that's the period, we can take the inverse of the period, as you recall, and that'll give us the frequency. So that's a good place to get. We're certainly not given that, but we can figure it out. Pi is pi. We know the mass of the spring. We know the mass of the weight. And that means we need to figure out the spring constant. So our first step here is finding the spring constant. Spring constant is 0.025 kilograms. That's the 25 gram weight, 25 gram mass, I should say, times 9.8, because we're trying to find the weight of that mass in newtons. So weight equation, mass times acceleration due to gravity gives us the weight in newtons. And the length of extension will be 0.05 meters. That's 5 centimeters. Divide it all out, we get 4.9 newtons per meter. So that means our spring constant for this particular problem is 4.9 newtons per meter. Second part of the problem now is we can combine these and plug them all into our equation here. So the period is 2 pi times the square root of 0.025. That is the mass of the mass, divided by the spring constant, which is 4.9, comes out to be 0.45 seconds. Now that's the period. The question asks for the frequency. So we've got to take the inverse of that. That means 1 divided by 0.45, and we get 2.2 hertz. This kind of makes sense. The period is about a half a second, so we would expect about 2 cycles per second, and that's what we get, 2.2 hertz. All right, so now what happens if we change some variables? This is something that AP1 wants you to know about. So we have our basic spring equation here. What happens if we start messing with stuff? Now, if we increase the mass, since the mass is in the numerator, that means that the period is going to get bigger. That kind of makes sense. When you hang a larger weight off of a spring or attach it to a spring, the thing slows down. It still oscillates back and forth, but it slows down because the force applied by the spring is the same, but it's being exerted on more mass, so the acceleration is less, so the period is going to be longer. Now, conversely, if we have a stiffer spring, in other words, K gets bigger, more newtons per meter, that's going to make the period smaller, which also kind of makes sense. You put in a stiffer spring, it's going to vibrate back and forth faster. So AP does want you to be able to evaluate how changing these variables will tend to change the result. Now we're going to move on to pendulums, simple harmonic motion in pendulum systems. You guys know what pendulums are, and this assumes a a pendulum where the string itself has no mass. So all of the mass is hanging on the end of a string. It's the simplest version of a pendulum. There's a different equation that you use if the string actually has significant mass. AP doesn't care about that. It does exist. You'll see that when you get to college. Anyway, this is the equation for a pendulum. T again is the period. It's in seconds. 2 pi shows up there again. Square root shows up again, so they're very similar. This is where the differences come in. Capital L is the length of the pendulum. Now, this is from the pivot point at the top of the pendulum to the center of mass of the body that is swinging. Doesn't come into play very often, but that's the way it is. So it's the length of the pendulum is from the pivot point at the top to the center of mass of the object itself, and then G is the local gravity, acceleration due to gravity. So on Earth, that's going to be 9.8 meters per second squared. But if we were to go to Jupiter or the moon, this number would change, and it would change the period. This kind of makes sense. If you take a pendulum to the moon, it's going to slow down because gravity isn't pulling on it as hard, so it's going to slow down. So if G gets smaller, you go someplace with less gravity, the period is going to get longer. And if you increase the length of the pendulum, that's also going to increase the length of the period. A longer pendulum takes longer to swing than a short one. Again, you can see that from your own experience. All right, now let's see if we can plug in some numbers and do this. Suppose we have a pendulum and we find that it takes 1 second to go from one extreme to the other. So it's going to swing back and forth, and from one extreme to the other extreme is going to take 1 second. Now, first of all, that means that the period is 2 seconds, right? Because the period is always for a complete cycle. So if it says it takes 1 second to go from here to here, then it's going to take another second to come back, and the whole cycle is going to be 2 seconds. So this is going to be 2. You'll probably might want to follow along with this with your own pencil and paper, because I can't write this one down, unfortunately. So 2 is equal to 2 pi. And the square root of L over G, and what we're going to try to figure out is the length of the pendulum. That's our goal here. G is going to be 9.8, L is unknown, 2 pi is 2 pi, and the period is 2. So the way we hash this out is we're going to bring the 2 pi over to the left side, square the whole thing to get rid of that radical, then multiply by G, and we should have the length of the pendulum. Let me get out a calculator so we can do that. So we're going to start off, let's see, with 2. That's the period, that's the T. We're going to divide that by 2, and then we're going to divide that by pi. That brings the 2 pi over. Now we are going to square the whole mess, because we got to square both sides to get rid of this radical. So x squared. And then we're going to multiply that by 9.8, because that is the acceleration due to gravity here on Earth. And we wind up with almost exactly 1. Almost exactly 1 meter. 0.9929 meters is the length of this pendulum. It's almost exactly 1. So 1 second, 2 second period corresponds to a 1 second, a 1 meter long pendulum. I hope you understand that is purely a coincidence. That's just the way it comes out. But it turns out to be almost exactly 1 meter for a 2 second period pendulum, or a pendulum that takes 1 second to go from one place to another. This actually works out pretty well for clockmakers. It means that you just have to make your pendulum and a pendulum clock slightly less than 1 meter, and it makes 1 second per swing. Tick, tock, tick, tock, and then it makes the building the gears pretty straightforward for making a timepiece that moves forward 1 second with each click. Okay, now what we're going to do for part B of this is, what if we take this same pendulum and we take it to the moon? Same mass, same length, we take it to the moon, and what happens to the period if we do that? All right, let's see. I think I have it on this. Yeah, I think this is the right numbers. I worked it out once before when I was getting ready for this, and I think that this is right. Anyway, you set it up the same way. Period 2 pi equals 1, because it's 1 meter long, divided by 1.625. It turns out the gravity on the moon is about 1/6 of what it is on Earth. Do the math, that comes out to be about 1.625 meters per second squared. Plug it all in, do the math, and you wind up with a period of about 4.9 seconds. If they want to know the frequency, then as you know, you take the inverse of that. Inverse of 5 is about 0.2 hertz, 0.2 hertz. And that's that. So make sure you can run through that. Now, last thing, I was talking about what happens when we change the variables in this. What if we change some variables? And I already talked about the length of the pendulum and the value of G. But one thing that I didn't point out that matters, mass does not matter. Nowhere in this equation does the mass of the pendulum show up. So if you have 10 kilograms on the end of a 1 meter long rope, it will have the same period as if you put 5 ounces on the end of a 1 meter long rope. As long as the rope itself has no mass and air resistance isn't significant, the only thing that determines the period of a pendulum is the length of the pendulum and the local value of G. Galileo was the first one to realize this, and so he made the first pendulum clock. Very crude one. Basically, he just counted the swings of a pendulum because he realized that it did not matter how much mass you hung off of it. As long as it's swinging, it will always be the same period. Now, one last caveat on this for pendulums. A pendulum, for this relationship to be true, the pendulum cannot be swinging very far. We take advantage of what's called the small angle approximation, meaning that if the angle of the pendulum is relatively small, like 5 degrees or less, then this expression remains true. What happens is if you go past 5 or 10 or 15 degrees, then the string is pulling in one direction and gravity is pulling in another direction. And the force of gravity, you have to take the sine or the cosine of an angle to figure out the actual force of gravity working against the string. Now, as long as the angle, like I say, the angle of the string is less than about 5 degrees, then the sine of that angle is basically equal to 1, and gravity remains constant. The force of gravity remains constant on the mass in terms of the balance of the tension of the string. If you pull the string like horizontal or at 45 degrees, then that relationship kind of goes away. And it doesn't work as well. And then this expression doesn't work. So bottom line, when you're using this equation, you have to assume that the pendulum is not being pulled to the side very far. Now, on AP questions, they will add in some verbiage like a pendulum, which is pulled only a few degrees to the side, blah, blah, blah. Here's the rest of the question. And they put in that phrase because if you go past about 5 degrees, then it starts to get a little bit more complicated. And they don't want you to have to worry about, well, you have to use calculus basically to work out the expression of how gravity changes in terms of the pendulum. We don't want to do that. So small angle approximation, keep the swinging less than about 5 degrees. All right, so what did we cover today? I think we're about done. We were supposed to do comparing graphs of simple harmonic motion. We did that. We talked about energy in simple harmonic motion. That's good. Introduced the spring equation, the pendulum equation, gave you some examples of each, and talked about what happens when you change the variables. All right, that's good. There will be some homework problems up on the assignments page, and we'll then be able to move forward.